I know I start each of these videos talking about the fact that we're building on what we did with electric fields with electric potential. But we just spent a lot of time learning certain techniques, and I think it's important to stress that we're just extending those and building on what we've learned and extending it and applying it in a slightly new situation. So just to recap, when we have an electric field from a point charge, we can then say that every little tiny element of our charge distribution, dq, is so small it acts like a point charge. And we can treat it like a point charge and integrate over our charge distribution to find the electric field. We can also do something similar with electric potential. The electric potential from a point charge can be extended to a charge distribution by treating each little tiny element dq of our charge distribution like a small point charge and integrating over the charge distribution to add up all the contributions. Then we said we also have another technique for finding electric fields when we have certain symmetry in our problem. When we have spherical, cylindrical symmetries or infinite sheets, then we can use Gauss's law to find the electric field. Well, in those situations, it's fairly easy to find the electric field. So in those situations, after we find the electric field, we can then integrate it over some distance to find the potential difference between those points. Of course, that only gives you a potential difference. So you'd have to be given where the potential is zero. Then you can start at that location and work your way in or out and find the potential everywhere with respect to the zero that was given in the problem. In the case where we have a uniform electric field, a constant electric field, this integral just becomes the electric field times the distance. How do we create a uniform electric field? Well, if we have two infinite sheets of charge, one with positive charge and one with negative charge, the area between those sheets would have a nice uniform electric field. If there's a potential difference of V naught between these two plates, and I told you that the rightmost plate was 0 volts, then you would know that the leftmost plate would have to be positive V naught. It would have to be that many volts higher than the right plate because our electric field points in the direction of lower potential. The potential on the positive plate has to be higher than the potential on the negative plate. And if we know the potential difference is V naught, and we know the right one is 0, the left one has to be positive V naught. What if I told you the potential on the left plate, the positive plate, was 0? What's the potential have to be on the rightmost plate, the negative plate? It has to be V naught lower than the positive plate because it's in the direction of the electric field. What if I told you the potential was 0 exactly halfway between the two plates? Then we would know that the potential on the left plate, the positive plate, is positive V0 over 2, and the potential on the negative plate would be negative V0 over 2. There's a potential difference of V0 that was given, and once we know where 0 is, we know how to find the potential on each of those plates. Now, if we look at a point charge, the potential from a point charge we know is kq over r. And that's, of course, assuming that v equals 0 at r equals infinity. If we were to graph this, it just looks like this. It's a 1 over r function. As the distance gets smaller and smaller and smaller, as we get closer and closer and closer to that point charge, the potential approaches positive infinity. And as r gets bigger and bigger, as we get infinitely far away from our point charge, the potential goes to 0. The electric field points in the direction of lower electric potential. So a positive charge sends its electric field out toward infinity, and as we move in that direction, the potential gets smaller and smaller and smaller until we hit our minimum value at r equals infinity. Now let's look at what happens if that charge is negative. If that charge is negative, then we have a negative 1 over r that we're graphing, and the function looks more like this. As we get closer and closer and closer to the negative charge, it goes toward negative infinity. And as we approach infinity, it goes toward 0. The electric field always points toward lower electric potential. From a negative charge, the electric field points in from infinity to the charge. And as we move in from infinity toward the charge, the electric potential goes smaller and smaller and smaller, more and more negative. Electric potential is a scalar, so -5 is smaller than -3 is smaller than 0. Let's work another problem. This one will do with spherical symmetry. A solid insulating sphere, uniformly charged throughout its volume. We want to find the electric potential everywhere. First, we're going to find the electric field everywhere using Gauss's law, because we know that's fairly simple to do. Then we'll use the integral of E dot ds to find the electric potential difference. If we're outside of our spherical charge distribution, this just looks like a point charge at the origin. We could use Gauss's law to show that. We know that the electric field outside of our charge distribution is kq over r squared. And it's positive charge, so it's going to point radially outward. Inside of our charge distribution, we can use Gauss's law and come up with the electric field. The area of a sphere, 4 pi r squared, and we just have to figure out what q is inside of our Gaussian surface. We can use the charge density, the total charge over the total volume, multiplied by the volume inside of our Gaussian sphere to get the charge inside of our Gaussian sphere. So we end up with the electric field 1 over 4 pi epsilon naught q over r cubed times r. It increases linearly as we move out from the center. At the center of our sphere, it has to be 0, right? Because we have equal charge on every side. If we're right at the center of a spherical charge distribution, there's equal electric field coming from every opposite side of us, canceling out at the center. We know it has to be 0 at the center. And as we move out, it increases linearly until we get to the edge of our sphere, and then it drops off as 1 over r squared as we move away from the sphere. If you prefer to write it as k, we can write it in this form. And then, of course, it's a vector quantity pointing radially outward. We want to find our electric potential as a function of r as we move from r equals 0 all the way out to infinity. We'll start where we know what the electric potential is, at r equals infinity, because we know the electric potential there is 0. So here's our charge distribution. We're out here at r equals infinity, and we're going to move in to some other place. I'm just going to call it r. We know this is positive charge, so the electric field points radially outward. And we know that delta V is negative the integral E dot ds. Delta V is always final minus initial. And we know our E in this region of space is kq over r squared. We have a dr, and we have a cosine. We have a dot product between E and ds. ds, in this case, is pointing in. We're coming in this direction, but our electric field points out. So we have a cosine of 180 degrees here. Our direction we're going is one way, our electric field is the other way. We have a cosine of 180. So we have the magnitude of E, the magnitude of ds, and the cosine of the angle between them. We are integrating from r, our final position, r, to our initial position, r initial. Because r is smaller than r initial, you always integrate from a small number to a large number. And we know that v initial is 0. So v final, I'm just going to call it v at r, any r, is negative k q. We have a minus 1 from our cosine 180. We have an integral of dr over r squared, and we're integrating from r to r initial, which is infinity. I'm just going to put infinity here. Remember, I said getting your minus signs correct is tricky. Getting it all correct is tricky. Let's just see how we did, and in the end, what do we know the potential has to be? The left side of the equation has to be what? Negative or positive? It has to be positive because we're starting at 0 at infinity and we're going opposite the electric field. So we have to be going to higher electric potential. What's higher than 0? A positive number. So in the end, we'll check to make sure we get a positive number. If we don't, we'll fix it. The minus signs here cancel out. I have a k, a q. Integral of 1 over r squared is negative 1 over r. And I am integrating from any r to infinity. That would be 0 minus a negative 1 over r. So this is positive kq over r. That's positive. The left side of my equation is positive. The right side of my equation is positive. Everything checks out. I can move on. I don't have to throw a minus sign in there. Get in the habit of thinking about your answer and seeing if it makes sense. Now you may have noticed already, this potential is the potential from a point charge. kq over r is the potential from a point charge. So if we're outside of a spherically symmetric charge distribution, as far as the electric field is concerned, it looks like a point charge at the origin. The same is true for electric potential. This looks like a point charge at the origin. Total charge, capital Q. Now we have to figure out what happens where the electric field changes. It changes at the surface of the sphere, and as we move in from there, we have a different electric field, so we have to do a different integral to find the potential there. We'll start at the surface of our sphere and integrate in from there. So the potential at the surface of our sphere is kq over capital R. And if we start at the surface and work our way in to some other location, this would be R final. I'm just going to call it R, any R between 0 and capital R. This would be R initial, which is capital R. And of course, the electric field, if this is full of positive charges, the electric field points radially outward. So I'm going to use my equation, delta V minus the integral of E dot ds. This is V final minus V initial. V final I'm just calling V little r, right? Any r. Could be anywhere from 0 to capital R, any r. V initial I'm going to call V capital R, right? That's at the surface. That's where I'm starting, at the surface of my sphere, and we're moving in from there. And now I'm going to plug in what I know for my electric field. I know my electric field is kq over r cubed times r. That's the electric field. My ds, we're moving in, but it's just has a magnitude of dr, and I have a cosine of 180 degrees because my ds points radially inward, but my electric field points out, and I always integrate from a small number to a big number. So in this case, it's my final r to my initial r, small r to big R. Okay. What do I get when I do this? We have V at any r minus V at the surface. The constants come out. We have a -1 from the cosine of 180. And the integral of r dr gives us an r squared over 2, evaluated from r to capital R. And so I get the minus signs cancel. And let's think about our signs now to see if we got them correct. On the left side of my equation, I have the potential at any location inside of the sphere minus the potential on the surface. The electric field points from the center of the sphere outward. So any point inside of the sphere has to have a higher potential than the potential at the surface of the sphere, because we're going against the electric field as we move in towards the center of the sphere. This must be positive. V at any r inside of our sphere has to be greater than V at the surface because the electric field points from the center to the surface. Let's take a look at the other side. We've got some constants here. Those are positive numbers. And we have a capital R squared minus a little r squared. And the capital R is bigger. It's the full radius of our sphere. The small r is some point inside the sphere. So this is a positive number. So all these numbers check. Our signs work. We can move on. If there was a negative number on the right side of this equation, I would just multiply the whole thing by -1 to fix it. We want the potential at any r. We want this number all by itself. So that's going to be everything on the right side of the equation. I'm going to pull the 1/2 out. And I'm going to bring this guy over to the other side. And I know what that is. The V at the surface of my cylinder is kq over capital R. So there's my potential anywhere inside of my spherical charge distribution. Let's plot this and see what it looks like. Here's our sphere, radius r, the electric field as a function of r, and the electric potential as a function of r. The electric field starts at 0 and increases linearly until you get to the surface of the sphere, and then it drops off as 1 over r squared as you move away from the sphere. So the electric field inside is proportional to R, and the electric field outside is proportional to 1 over R squared. The potential when we were outside of the sphere dropped off as 1 over R as we moved away from the sphere. But when we moved inside of the sphere, it was proportional to negative R squared. That means it looks something like this. V is proportional to negative R squared in this region here. What is it at this point, at the surface? The potential is K Q over capital R, the radius of our sphere. And what is it at the center? When we put R equals 0 in there, we get 3/2 K Q over R. Where did I get that? I just put R equals 0 into my equation and I solve for it. So a quick recap. We find the electric field everywhere because we had a nice symmetry in this problem, spherical symmetry. We knew it was very easy to find the electric field everywhere. We start where we're given the potential is 0, and we integrate our electric field, E dot ds, between that point and any point we want. We usually just let it equal R and a variable. And then we get our delta V, and that usually gives us the potential as a function of R. We can keep doing that all the way to the point where the electric field changes to something else. And then we have to stop, and we have to do a different integral of E dot ds where the electric field has changed. That's why I stopped at the surface of our sphere, and I did a second integral inside because the electric field is different inside the sphere as it is outside.